Hello, in this video I would like to go over a simple limiting reactant problem like the one we saw in class today and walk again through the different steps. So here we have an example where we have a reaction of 5 grams of magnesium metal with 10 grams of oxygen to form magnesium oxide. What is the limiting reactant and what will be the excess reactant? And what is the mass of the magnesium oxide product that is produced? We want to know that as well. And what is the mass of the excess reactant left over? So we only want the identity of the excess reactant. We also want to know how much of that will we have left over. So always with these word problems, we need to come up with what's being given and what's being asked. And in this case, the first thing we're being given is a word equation right here that we need to convert to a balanced chemical equation. So we've got magnesium metal reacting with oxygen to form magnesium oxide. So we have here then magnesium. So we've got magnesium metal reacting with oxygen. And oxygen is a gas unless given otherwise. And this forms magnesium oxide. And I did that demonstration in class about 2 weeks ago where I burned a strip of magnesium metal and it makes a very bright, it's a very bright exothermic reaction, gives off a lot of heat and light. It actually was used in the old days in part of flash photography. So there'd be like this magnesium dust that would get ignited and make this bright flash of light, and then but it would always cover all the people being photographed in a layer of ash and soot. So you might see that from some of those turn of the last century movies where they have the big flash bulb that goes poof and a bunch of smoke goes out. So anyway, magnesium oxide is produced, and this is a white chalky solid and an ionic compound. Now we always need to do a balanced chemical equation. So we see right here we've got 2 oxygens, only 1 over here. So let's balance that with 2. And then we also would need 2 magnesium. So at this point now we have a balanced chemical equation. So now we need to figure out, okay, how many moles of magnesium? So we've got grams of magnesium and grams of oxygen. Now this chemical equation only speaks in the language of moles. So we need to convert these grams of magnesium to moles of magnesium, and these moles of oxygen or these grams of oxygen to moles of oxygen. So let's start off with the number of moles of magnesium. So we then just calculate that by having the 5 grams. 5 grams of magnesium, and divide that by the molar mass, or in this case the atomic mass. It is 1 mole of magnesium is 24.31 grams. And if we calculate that, we end up with 0.2057, and it's usually a good practice to carry extra digits as you're doing intermediate calculations. So I know that we only have 3 significant figures given here, but in this case it's good to carry 1 extra digit when you're doing these intermediate calculations so that you don't lose any information when you're rounding as you do more calculations. So then people have the custom to write the last digit a little bit smaller or so to indicate that at the end you're going to drop that 1 or round it up. But for now, let's carry that. And so we have 0.2057 moles of magnesium. And likewise, we have the number of moles of oxygen that we can calculate. We start off with 10 grams of oxygen. And divide that by the molar mass of oxygen. Again, oxygen is 1 mole O2 is 32 grams. Equals 0.3125 moles of oxygen. And again, I write the last number here a little bit smaller and sort of offset on purpose. So then we can figure out from this balanced equation right here, we can see we have 0.2057 moles of magnesium. We can use this number right here to figure out how many moles of oxygen we would theoretically need. So from the number of moles of magnesium, we can find out the number of moles of oxygen needed. would be, so we start off with 0.2057 moles of magnesium, and then we use our stoichiometric coefficient right here, so we know for every 1 oxygen we need 2 magnesiums, and so that means we end up with, so now the magnesium cancels out and we end up with 0.1029 moles of oxygen. So this means right here, to react the magnesium that is available, these 5 grams of magnesium, we would need 0.1029 moles of oxygen. But we have 0.3125 moles available. So we have more oxygen available than we actually need to burn all this magnesium. So we can conclude already, right here, without doing much anything else, that oxygen is in excess. So we can conclude that oxygen is in excess. And therefore, that means that the other reagent is going to be limiting. But we can prove that as well. Okay, so the other reagent is going to be limiting, so magnesium is limiting. So let's do that next. Let's see how many, from the moles of oxygen that we have available, how many moles of magnesium we could react. So we could do that as well. So if we have the number of moles of magnesium that we need, so we start off with 0.3125 moles of oxygen, and we then assume, okay, how much magnesium would this all use up? Number of moles of magnesium equals and so this would be the number of moles needed. Sometimes good to write that in the little note below it so that you know which one you're calculating here. So we start off with 0.3125 moles of oxygen that are available times, and now we again use the stoichiometric coefficient, so which is 2 magnesium for every 1 oxygen. And so the oxygen now cancels out, and we're left with 0.625 moles of magnesium. Now, this again shows what we just were illustrating earlier. So we basically would need, so this amount of oxygen right here could burn through 0.625 moles of magnesium, but we only have 0.2057 moles of magnesium. So we could have a lot more magnesium burned up in this experiment, but we don't have it available. So again, we can say that the magnesium is limiting. Okay, so we have, so 0.625 moles of magnesium are would be needed to use up all the oxygen. Or use up the available oxygen. So the 3125 moles of oxygen would require 0.625 moles of magnesium, but we only have a smaller amount available. So we only have 0.3125 available. So we only have, make sure we write that down, only have 0.3125 moles available. So therefore, we can conclude again, magnesium is limiting. Okay, so another way to conclude that. So if you end up calculating it this way around, you can do the same thing right here. Find out, okay, you know that the magnesium is limiting, and we've got an excess oxygen. So you only need to do really one of these two calculations to get to that answer. Now, the next thing right here is finding out how much of oxygen is left over. So mass of oxygen left over. Let's calculate that here. And so then we really just need to find out, okay, the number of moles of oxygen available minus the number of moles of oxygen needed. And so we started off with, we have 0.3125 moles of oxygen available minus the 0.1029 moles that we need. So we said we only need 0.1029 moles of oxygen to actually complete this reaction. And so that is then going to be the and so then this would produce 0.2096 moles of oxygen left over. Now we can convert those to grams, so we then have the mass of oxygen left over. And this then is 0.2096 moles. And divide that by, multiply that by 32 grams per mole. So 32 grams of oxygen for every mole of oxygen. So, and if we do that, we end up with 6.7007. So since we're dealing with this now, this is really sort of our final answer here. So we can write this up 0.7, or we can write this as 6.71 grams of oxygen left over. And then the last answer that we want here is what mass of excess reactant is, we already calculated what is the mass of magnesium oxide produced. Okay, so that's the last thing that we need to do right here. And we can then find the mass of magnesium oxide from the limiting reactant, and which is magnesium. So the mass of magnesium oxide produced, and we can calculate from the limiting reactant. And let's do that, the mass of magnesium oxide. And so we start off with the 0.2057 moles of magnesium. And from the reaction stoichiometry, we see that it's 2 magnesium oxides that are produced for every 2 magnesium. So it's really 1 to 1. And we can here do this all in one step here, and then convert this to grams, which is what we're really interested in. So the molar mass of magnesium oxide is 40.31 grams of magnesium oxide divided by the moles of magnesium oxide. And if we calculate that, 0.2057 times 40, we end up with 8.29 grams of magnesium oxide produced. It is then worth noting, you can always check whether you've got anything mixed up or so, that the total masses should add up to the original masses. We're still following the conservation of mass. So we started off with 5 grams of magnesium with 10 grams of oxygen. All the masses that we have calculated so far should add up to 15. Okay, so we have 8.29 grams of magnesium oxide that are produced. All of the magnesium has been used up, so we don't need to worry about that. But we said we have left 6.71 grams of oxygen. If we add those two together, 6.71 plus 8.29, we end up with 15, and that confirms the result. Now, one last thing to clarify right here is to make life easy. It's often good to do a little check right here in the just looking at the stoichiometric ratios. So what you can just do, to save time, you can just look at, say, the ratios of masses and moles. So say, for example, use mole ratios to find the limiting reactants. Now, this technique will not tell you how much is left over. You still need to do these calculations that we just did. But if we say, for example, we start off with 0.2057 moles of magnesium, and the ratio is 0.3125 moles of oxygen. And we look at the stoichiometry for we see it's 2 magnesium over every 1 oxygen. So that means right here we've got the 0.658 if we divide these two numbers right here, and that is obviously smaller than 1. Okay, so that means that in this case, that this denominator right here is dominating, and so therefore that means that the oxygen is in excess and magnesium is limited. So in general, you can look at this, and so we were just looking at this at the mole ratios from the stoichiometry, so you can look at the number of moles of A over the number of moles of B, and if this is smaller than the stoichiometric mole ratio of A over the ratio of B, of compound B, then you know if it is smaller, that means that B is in excess and A is the limiting reagent. And likewise, you can flip this upside down and do this the other way around, and you can also say number of moles of A over number of moles of B, and if that is now larger than the stoichiometric ratio, over the stoichiometric coefficient B, coefficient, here I need to write a little bit slower with this tablet, coefficient of B. So if that is smaller, then we know that B is then limiting and A is in excess. Anyway, so here another question for you, and in a quick video, and I hope you found this informative, and thanks you for watching. Have a great rest of the day.